Okay, so we are now on the part of designing the column. That is designing the gas absorption or the stripping column. For a packed column, so you have your column here. This is a representation snipped from our textbook. The liquid, of course, is entering the topmost part of the column. The gas is entering the bottom part of the column. And in the case of the packed column, you have, of course, packing materials inside. That would ensure that your liquid and your gas are intimately contacted. And actually, the interface is produced or formed in the packing material. So speaking of the packing material, we have two types, and we will go to each of these two types of packing material. So in here, I have the different packing materials, and specifically the random packing material. So you have like 16 different types of random packing material here. On the other slide, in the next slide, you have the structured packing material. So you have the FlexiPaks, you have the FlexiPak ceramics here, you have the Millapaks, and you have the Monts. So these are just but examples of structured packing material. So when we design our column later, you will learn that the type of packing material used really has a vital role in the contacting of our liquid and gas phases, and as such, in terms of the design of how big our column is, and that has something to do with the diameter, we really consider the type of packing material to be used. Now, I have here a video I got from YouTube from Al-CHE. So hopefully you get to see this in terms of how the liquid and the gas phases in the gas absorption column are contacted through the use of this packing material here. So please watch. Okay, so as you could see in here, we have the application of gas absorption in cleaning up a gaseous stream. So a gaseous stream which has the presence of a contaminant. So the purpose of the packing material is for contacting actually the liquid and the gas phases, as you can see in the video. Now we also have, aside from the packed tower, we have the tray tower. So in here, we don't have the presence of the packing material, but rather we have the trays. So I have here a section of a tray tower in the illustration. And this is the tray. The liquid goes down, flows horizontal here on the tray, then goes down again, then flows horizontal on the next tray, then goes down. So it's like a zigzag motion, and the gas, however, flows up. Okay, so they are flowing countercurrent to each other. The same purpose, the gas, which is your feed, will have to be cleaned. In the case of a gas mixture that has the presence of a contaminant, will be cleaned by your solvent, which is liquid. So this is in the case of the tray tower. So you have this, we call this, by the way, downcomers. I've mentioned this in our last discussion for those who have already met uh, uh, separation process before as a course, and downcomer was already mentioned. This one is the downcomer apron. It guides the liquid through the downcomer. Now, in terms of the tray tower, if in the case of the packing materials, we have two, and they are classified either as random or structured packing material. In the case of the plates, they can be perforated in the case of what you see here on the left. And you can have the bubble cup or the valve cup. This one is the bubble cup. The bubble cup, you will see later what's its difference in terms of operation as compared to the valve cup. And these are your tray with valve cups already. So the openings in our tray can either be any of these three. Okay, so in the case of the tray tower, and these are the different valve openings for the tray tower. Now, I have here a video for the different types of openings on the trays of our tray tower. I'd like you to look at it because it's a simple simulation of what's really happening inside the tray column, specifically on the tray, based on the different types of openings that it may have on the tray. Okay, so as you can see, it's really using the bubble cup is really economical. Economical in the sense that probably in terms of design, it's not economical because of labor cost in installing the cups, as discussed on the video. However, in terms of the bulk of gas mixture that it can process, as you can hear from it, it can process a very large volume of gas with a very little amount of liquid solvent needed. So in terms of liquid solvent requirement, if it's really very costly, the initial cost of having to use this particular type of tray tower, the bubble cup tray tower, would still be advantageous over the other types of tray openings. So let's look into the other types of tray openings. So that one is the valve tray. The bubble tray is bigger than the valve tray, though in the case of the valve tray, it's the one that goes up whenever there's already a buildup of pressure underneath the tray to ensure that there is less whipping When we speak of less whipping, no liquid will pass through the holes in the tray. So that's a new term for you. And I remember asking the class during our discussion before that they have to look into the meaning of the terms that I'm using. So when we speak of whipping, it's when the liquid goes through the holes, not through the downcomer in your tray columns. So that's whipping. So in the case of the valve trays, it's the valve that rises, compensates for this whipping when pressure builds up below the tray. In the case of the previously discussed opening, the bubble tray, there are cups that cover the holes, whereas in the case of valve trays, there are no cups. But still, in terms of use, the bubble cup is often used on the valve tray. There is another one, I guess. Let's see if this is the one. Mm, mm, So the simplest of the three, the bulb, the valve, the bubble cup, the valve, and the sieve tray is the sieve tray. So there's no other, there's no cup, there's no valve that goes up. It's very simple way of contacting the liquid. However, due to the simplicity of its design, if you're listening really closely to the video, whipping is a problem. And that is the liquid, instead of going across the tray through the down cover, going down the column, it goes through the holes in the tray. And that would be a big problem in terms of recovery because your solvent is not going through the channels in which you pass through. It should be passing through in the case of the process of gas absorption or stripping. So that's it, the three opening on the trays of a tray tower. Now, let's go to the meat of this topic. So we are now ready to design our column. And that is, when you speak of design, it has something to do with the diameter and the height of the column. And these two, the most tedious part actually is in determining the tower height because of the several equations that needs to be used before you can reach the final formula that will lead you to the Z. The diameter, in determining the diameter, we are using empirical equations and graphs so as we could determine the necessary size of our column. Now, the way we design the diameter of our column, I think you know already this one. It's based upon the flooding velocity. And we are also taking into consideration the pressure drop, and the tower diameter can be computed out of knowing these two. Now, the usual design, if you're going to base it on the recent edition of Unit Operations book as prescribed by PRC, is that we are to use 60 to 80% of the flooding velocity in computing for the tower diameter. In old books, but the meaty ones, when it comes to problems that are being discussed and given, 50% is already okay. But in our case, we will depend on what is stipulated in the problem. So if the problem specifies that it's 60%, do so use 60%. If the problem is silent, whether it's 60% flooding or 70 or 80%, we have to use the conventional one. And that is, we use the 50% flooding velocity and computing for the size of our column. So the problem specifies it. So if it is not specified, we use 50%. As for the flooding pressure drop, as the term implies, this is the corresponding pressure drop inside the column caused by flooding. So when flooding occurs, then the pressure inside the column is going to drop, and there won't be enough pressure to make the gas go up and the liquid go down. So what happens is the liquid will pass through the hose because the pressure of the gas is not enough to push the liquid up the hose, especially in the case of the tray towers. So the formula is very straightforward. The delta P, or the change, or the delta P, change in pressure or pressure drop at flooding, is 0.0115 times the packing factor raised to zero point 0.7. In your handbook, probably this is 0.12. So anyway, a 0.115 and a 0.12 will not be really differing in terms of the answers later on that you will be getting. So it's very straightforward. However, when we determine the column diameter, this is the outline procedure of finding the diameter of the column. So we get the packing factor from a table. It will be shown to you later. Then we determine the flooding pressure drop based on the formula just presented. Then we find the corresponding gas velocity, the usual linear velocity for the gas, so that it's in the, let's say, on the region of about to be flooded. So meaning it has to be lesser so that it won't be flooded, is 6.6 feet per second. And that's around 2 meters per second. And we chose diameter for such gas velocity to be half. We choose diameter such that gas velocity would be half of this 6.6 feet per second, or 2 meters per second. Now, the typical design would be, it's a very conservative one, is only 1 meter per second. So it's half. So just like what I mentioned a while ago, that the flooding, the tower diameter is based on 50% of the flooding condition. So the linear velocity of the gas at flooding is also in this case divided by 2. After that, we find the pressure drop in the column from the pressure drop correlation figure. So it will be shown to you on the next slide. So as for the packing factor, your handbook gives you a more detailed, comprehensive set of tables just for the packing materials only. And you will find in that table the packing factors. I only got a sample, and the similar one is found in John Copley's. And in this column, you can see the packing factor in the unit of per foot, and this one is per meter. So it depends on the type of packing material you're going to use. So you look for the type of packing material here, and you find the corresponding packing factor. So they are already here divided or categorized in terms of random packing and structured packing material. Now, so that's where we get the packing factor. Now, as for the pressure drop correlation, so after you have determined the pressure drop, we cannot determine the linear velocity at flooding, and that's the V that was mentioned in the last 2 slides, when we do not know the pressure drop. So these lines here, or these curves here that you see, are actually the delta P's. And we determine the abscissa, or the x coordinate of this particular graph. By the way, this is an empirical graph, and we will find the corresponding capacity parameter here on the y-axis. So we need 2 data, the delta P and this flow parameter, so as to be able to get the capacity parameter. Now, the capacity parameter gives us the linear velocity, the one that I'm pointing to. This is the linear velocity. And the rest of this one are taken from the appropriate table. So we have the density of the liquid and the gas. We have the packing factor here. We have the kinematic viscosity, which will use the viscosity and the density in that case. Now, this is in the case of the random packing material. So we'll be using a different graph when we are to use the structured packings. It looks similar than the first one. However, of course, empirically, they are not of the same construction. So in terms of just the way they look similar. So procedure is still the same. Only we're using a different table. So this one is the exact sample problem that was taken from John Copley's. Please bear with me. I scanned it directly because it's really so hard to write down equations using the equation editor now and having to deal with Canvas with such a concern. So I think most of you have already encountered this. So I will just simply read through and outline the procedure that was discussed in here and how to use the diagrams and the table I just pointed out. So in this problem, we have ammonia, which is to be absorbed in a tower using pure water. So you're given the temperature and the operating pressure of the tower. So the feed rate is given in terms of the English and SI unit, and it's a mole fraction of ammonia. So we are safe here in saying that our air is contaminated by ammonia, and we want to scrub off ammonia from the air ammonia mixture. So the process design here specifies a liquid to gas flow rate ratio, and that's the GL and the GG, or simply the L over V, of 2:1. And the use of, so the packing material that is specified is the 1-inch metal pall rings. So in letter A, you are to calculate the pressure drop in the packing and then the gas mass velocity at flooding. So when we speak of gas mass velocity, it's the GG, or the G sub G. The linear velocity is simply the V. So the gas mass velocity at flooding, meaning the answer that you're going to give here is it's flooded already. The column is about to be flooded already. Now, in that particular value of the gas mass velocity, you are only to use 50%. So 50% of the flooding velocity, and calculate the pressure drop if you're going to use only 50%, and determine the gas and liquid flows, and correspondingly design how large a column you would be needing in this particular problem. So it's saying here that I have 10 minutes. So that's for letter A. And for letter B, you are to repeat the procedure in letter A using the Millipox 250Y structured packing. So then common sense would tell you then that letter A is giving us a structured packing, a random packing rather, in the form of a 1-inch metal pile rings. Now, this is not the usual way we solve problems in determining tower height or even the pressure drop, because as I have told you, we always start with what is required. So you have already, let's say, identified all the given information and you determine what is required. So based on what is required, the first one that is stated here is the pressure drop. And after the pressure drop, you have the gas mass velocity. And after that, the liquid flows and the tower diameter. Those are the things that we need to determine. So the solution that is outlined here is based on the author of the book, which already knows the problem that he is giving. So he knows what data he is needing. So in your case, you can always start off with the formula, and then from the formula, find your way through the required information that you would be needing. So in this problem, class, later on, you will notice that you will be needing the average molecular weight, okay, average molecular weight of the air ammonia mixture that enters the column or the scrubber. And that could be determined by multiplying the molecular weight of air, which is 28.97, which can be approximated to be 29. And since we have a 3% mole ammonia in air mixture, then your air is 97%. The 3% will be your ammonia. Now, this 28.61 is the average molecular weight of your air ammonia mixture. You will be needing this in a little while. So it's already predetermined here. If you will be needing the average molecular weight, you will also be needing the weight fraction of ammonia. The weight fraction of ammonia later on so that you can account for the actual gas and liquid flows to your tower. So in this case, how do we find the weight fraction of ammonia? Take note, it's weight fraction. Now this one is mole fraction. So then what you're going to do, this mole fraction of 3% ammonia will be multiplied to the molecular weight of ammonia. Molecular weight of ammonia to its mole percent. Then that would give you the mass of ammonia in the numerator. And then you divide it by the total mass, or that's the average molecular weight of the mixture. So you have 28.61. This one, the denominator, has a unit of mole, or rather gram per mole, and this one is also gram per mole. 0.03% of the molecular weight of ammonia, which is 17. So both has the same unit of moles. So anyway, they will cancel it out, giving you a weight fraction of ammonia, which is 0.01783. Now this one, I did not suggest that this particular formula you use for finding the density. I suggest a much simpler way of determining the density of your ammonia air mixture. And that is from your thermodynamics. Let me just review you on this. That's pressure times molecular weight over the universal gas constant times the divided by as well the absolute temperature. Although this particular formula gives you the same answer, but if you're going to process it, you're going to process or determine density using PM divided by RT formula, the same answer you will get. So later on your own spare time, we do this using the procedure that I gave. Of course, you have to make sure that you're using the correct universal gas constant that should give you a unit for density in pound mass per cubic feet, while at the same time having pressure units in ATM and temperature unit in Rankine, because if you notice, this one is Rankine already. Okay, so this 77 is actually the Fahrenheit temperature equivalent of the 25. So if you notice, when it's the author that writes the answer, it's straightforward, doesn't contain the unit, it just contains the final unit. So find your way through. Again, redo it during your spare time, determine the density using the formula I gave. Now, the parameters that you need get from your property table, so it's of course suggested here that it's going to be taken from the appendix, but in your case, you have to get used of finding it from the handbook. So I suggest you find your way through your handbook, section 2, excuse me, and try to find the following parameters for water. So you have viscosity in centipoise, density of the water, and then determine the kinematic viscosity, as I have mentioned a while ago, in terms of the viscosity that you got here divided by the density of the water. That would give you a unit in centistokes. As for the packing material, which is 1-inch power rings, all you have to do is get it from the table, and you can right away substitute to the formula the packing factor. That way you will have the corresponding pressure drop. Now, since it's an empirical formula, I'm referring to this. The unit is, of course, as is where is. So the unit of the pressure is inch water per foot of packing material. If you intend to change it, then you have to use the proper or the appropriate conversion units. So this is the unit that you will be getting out of this particular empirical equation. For those who were just taking this for now, for metal pile rings, this is metal pile rings 1 inch, you get the packing factor here. Okay, so 56 for per foot, and if it's meters that you will use, you will have the 184. Let me see. So that's for the metal pile rings. It's 56. Okay. Now, You already have the pressure drop. I will be cut in 2 minutes. You already have the pressure drop in here. So you have to determine the x-axis coordinate or the abscissa of the what? Of this. So this one is for structured packing. So you have to use this graph. You have to solve this specifically together with the value that you're getting here and the pressure drop curves here. Correspondingly, you use the value that you got, you'll be able to get the capacity parameter. So that's what's done here. You solve for the abscissa, and that should be 0.06853. And this abscissa, together with the pressure drop that you got, the value of which is 1.925, you read the corresponding capacity parameter on the vertical axis of the graph, and that's more or less around 1.7. So how do you do that? You look for the 0.0683, it's somewhere here, and then you look for the 1.92. You don't see it here, but you approximate. If this is 2 and this is 1.5, then 1.92 must be somewhere in between these two. And then read here, project on the left the corresponding value of the capacity parameter. So the problem gives us that it's around 1.7. With that, you'll be able now and you're ready to determine the linear velocity. Why? Because everything here you need to substitute. You already determined the density. You already have the density of the liquid. You already have, again, the density of the gas on top. You have the packing factor. And you have predetermined the kinematic viscosity. So you have substituted everything. You will get this linear velocity. So far, you have only answered the first question, and that is the pressure drop. The next question is the gas mass velocity, and this is it. The gas mass velocity is the product of the linear velocity of the gas, which you just solved using the curve and the values that you got for the abscissa of that curve and the pressure drop. And you will have a value for the gas mass velocity of 0.4870 pound mass per second feet squared. This value says that it's already at flooding condition, meaning that